Assalamualaikum. Okay, Assalamualaikum. Okay, I would like to discuss one example, trust analysis. I want to show to you how we want to establish the structure stiffness matrix for trust. Okay, before that, I want to highlight some important things. Number one, as I mentioned last week, node is join and element is member. Number one. Number two, nodes and element represent by numbers. Okay, conventionally we use ABC to represent nodes and to represent join and member. But now in stiffness method, we will use number in order to represent nodes and element. Number three, truss has 2 degrees of freedom in x-axis and y-axis. In this direction, this is positive x, this is positive y. Beam has 2 degrees of freedom per node in y and z axis. This is for beam, this is y, this is z, positive z. And frame has 3 degrees of freedom in x axis, y axis and z axis. X, y and z. This is x, y and z. This is positive direction. One node is actually one point or one joint. Two nodes is one element. It cannot be more, cannot be less. It must be two nodes. Combination of two nodes become one element. And combination of many elements is called as structure. Okay, for the element stiffness matrices, element or member stiffness matrices, we use K, small letter of K, to represent element stiffness matrices. And for the structure stiffness matrix, we use K, capital letter of K, to represent the structure stiffness matrix. And size of the structure stiffness matrix is depend on the degree of freedom, total joint times degree of freedom for truss, for beam as well as frame. For example, if truss has 3 nodes, 3 times 2 means the truss has 6 degree of freedom in total. And size of the matrix is from size of the matrix for the stiffness is 6 by 6 matrix. Okay, after that, after we have established the stiffness matrix for the structure, we will apply the stiffness equation, or it also called as force displacement equation, okay, in order to determine the unknown displacement and unknown reaction forces. Okay, this is the basic equation where Q is nodal forces, Q naught is equivalent nodal forces, K is structure stiffness matrix, D is nodal displacement. Okay, all this for the structure we will use the capital letter, okay, to represent this. Okay, and number 13 we have all small letter. Qn is actually Q1, Q2, Q3. N is number of element in the structure. Okay, we use small letter to represent element stiffness matrix. Element stiffness, element. Sorry, this is not for element, this is just for member force. Sorry. Okay, for element for QN is for member forces. If the truss has 2 member or 3 member, so we will have Q1, Q2 and Q3. Okay. Okay, and Q0 is Q0 is equivalent element nodal forces. Okay, different between this and this is the one is small letter, one is capital letter. Small letter is to represent element and capital letter is to represent the structure. That is why in Q0 here there is no word, there is no element word here. But for this Q0 it has the word element because the small letter is to represent element. Kn means K1, K2, K3 and represent number of element in the system. Okay, it is called as element stiffness matrix. Okay, degree of freedom must be divided into constrained and unconstrained based on support condition. Zero displacement for support except support settlement. Constrained system, non-zero displacement for unconstrained system. Okay. Actually for the flow we will start with establish Kn, K for element. After this we will establish capital letter structure stiffness matrix, and after that we have to apply the equation Q is equal to KD. Okay, for the basic one Q0 is equal to 0, so this is the basic equation. So after we establish this structure stiffness stiffness equation or force displacement equation, we will establish unknown displacement, and after that we will establish the reaction at the support, and finally for truss we will determine Q. Small letter of Q means member force. This is reaction force. Unknown reaction force. This is unknown displacement. Okay, this is the first example in the textbook. Okay, example 14.0. The question is, okay, we go phase by phase. Okay, for today I just want to focus on this, how to establish the structure stiffness matrix. Okay, this one. Okay, let's look at this example given in the textbook. The question is determine the structure stiffness matrix for the 2-member truss shown in the figure. AE is constant. Okay, by looking at this question in diagram B. Okay, in this diagram we don't see any load here. We can only see the structure and the support. Okay, so before we start the analysis, what we need to do is number one, we have to make sure that we have labeled all the node number. Okay, we have node number 1, node number 2, node number 3, and in this question the node number have been given. Okay, step number 2, we have to label element number. And in this question the element number is also given. Element number, remember that element, what is the meaning of element? Element is two nodes combined together. Okay, so we have element 1, and element 2. For node number, we have node 1, node 2 and node 3. Okay, step number 3. Okay, number 3, this is the most important thing. Okay, this is the degree of freedom label. Okay, since there are 3, 1, 2, 3, and in truss there are 2 degree of freedom per node. So what we need to do is, okay, let's say like this. Okay, we have to divide the truss into 2 systems. The first one is called as unconstrained system. Unconstrained system, constraint DOF, and system number 2 is called as constraint DOF. Okay, or normally what I do is I will sketch the element, the structure like this, both for both system. Okay, and remember that we will label the unconstrained based on the support, based on support. And by looking at this diagram, okay, here is pin 2, node 1 is pin support, node 3 is also pin support. Okay, and we know that okay, support is constraint system, so we have, and pin has two degree of freedom. Pin reaction at support, at pin support is 2, reaction at pin support is 2, so we have to put here. Okay, there are 2 degree of freedom at 1, and there are another 2 at node number 3. Okay, what I can conclude here, this is the most easiest way to determine the degree of freedom in constraint system. It is equivalent to number of constraint DOF equal to number of unknown reaction in the truss. So conventionally there are 4 unknown reactions. So 4 unknown reaction. Okay, means that 4 unknown reaction equal to 4 DOF in constraint system like this. Okay, so since we know that total is 6, so the remaining 2 DOF we need to fill in the other system, which is unconstrained degree of freedom system. To end number 2 we put another 2. Okay, why we need to do this? If we want to remember the degree of freedom, we have to make sure number 1, we have to draw the unconstrained degree of freedom system first, then only constraint system. Number 2, we have to label the constraint first, because number of constraint degree of freedom is equal to number of unknown reaction in the truss, and I believe that everybody here have the ability to identify number of unknown reaction in the truss. And by knowing that, by doing that, if we know that there are 4 unknown reaction, we know that in the constraint system there are 4 degree of freedom. But since this has 3 nodes, times 2 DOF, so we get 6. So if 4 is located in constraint system, we have remaining 2, and the remaining 2 is located in constraint. In unconstrained system means at node number 2. Okay, so for the labeling, we need to label start from unconstrained. We need to label number 1, label number 2. Okay, this is 3, this is 4, this is 5, this is 6. Actually, we can also label like this: 3, 4, 5, 6, doesn't matter. It is just the matter of position. However, what we need to follow is we need to label unconstrained system first, followed by constrained system. Okay, we refer to the same label: 3, 4, 5, 6. Okay, okay, so we finish label degree of freedom. Okay, step number 4 is arrow. Okay, we need to put the arrow in order to identify near end and far end. Okay, that is the purpose to put the arrow, and we can put the arrow in any direction that we like, in any direction. In any direction, doesn't matter. Okay, in any direction. So like we can see here, the direction is this. Okay, for element number 1, this is the arrow. Element number 2, this is the arrow. Okay, and the arrow is parallel to the member. Okay, last thing that we need to do is we need to label, put the coordinate at each node. Okay, choose 0, 0 node. Choose 0, 0 node. Okay, here we need to choose one node as origin. We label as 0, 0, and by choosing 2 as origin, we can label node 1 and node 2. Okay, in coordinate system. Okay, in coordinate. Okay, normally we will choose node number 2, because if we choose 2 as origin, 3 will become positive coordinate, positive x and positive y. It is 3, 0, and for node number 1, the coordinate is 3, 4. 3, 0 and 3, 4, like this. Okay, so every time we before we start analyzing truss using stiffness method, we need to, number 1, make sure that the diagram has node number. Okay, number 2, we make sure the diagram has element number. Number 3, we must make sure that we label the degree of freedom according to unconstrained and constrained system. Okay, like this. Okay, we put X as number 1 followed by Y. 1, 2, 3, 4, 5, 6. Okay, step number 4, we need to put the arrow, and this arrow is very important in order to identify which is near end, which is far end. And the arrow we can put in any direction that we like, and the arrow we put must be parallel with the element or the member. And step number 5, coordinate at each node. We have to put coordinate. Normally we choose origin first. For this case, the origin is located at node number 2, and by having 2 as origin, node number 1 and node number 3 has all positive coordinate, X and Y. Okay, so after having all this information in one diagram like this is node number 1, this is node number 2, this is node number 3. Okay, this is 0, 0, this is 3, 0, this is 4, 0. Okay, for the degree of freedom, we have here 1, 2, here is 3, 4, and node number 1 is 5, 6, and node number, element number, arrow, and element number 1 and 2, 1 and 2. Okay, after having this, then only we can start to calculate element stiffness matrices. Okay, start with, now we want to establish this element stiffness matrices, means K1 and K2. Okay, for element number 1, the L is 3. Let's say I change all this to meter. Okay, L is 3 meter. L is 3 meter. So here I draw element 1, the diagram. This is node number 2, node number 3, 0, 0, and 3, 0. The arrow is like this, and the DOF. This is 1, 2, 3, 4. We have node number, element number, degree of freedom, arrow, and coordinate. So complete 5 information in this element. Okay, we will start with determining the Cx and Cy, or lambda x and lambda y for element. Okay, for Cx, okay, Cx is and Cy, we need to determine these two values, Cx and Cy. Okay, for Cx, please look at x value. For Cy, please look at y value. Okay, it must be far minus near. Okay, how to identify far? Because the arrow is going to far end. Arrow is going to far end. So from this we know that this is far end, this is near end. So far minus near is, far x is 3, near x is 0, and this will be divided with 3 meter by length, so it is equal to 1. For Cy, it is far y 0 minus near y 0 divided by L is 3, so this is equal to 0. Okay, so for the K1, it is AE divided by L. It is, the formula we can refer to the appendix given. Okay, the formula you don't need to remember. Just follow the formula given. Okay, it must be 4 by 4 matrix. 4 by 4 matrix. Why? Because in element there are 2 nodes, and 2 nodes has 4 degree of freedom, so it is 4 by 4. Okay, it is CX. Okay, by looking at the formula, it is CX square. Okay, here I want to put L. L is 3 meter. Okay, 3 meter. CX square means 1. CXCY 0. Negative CX square is negative 1. Negative CXCY is 0. Okay, then since the matrix has the symmetry characteristic, so 2 1 1 2 is equivalent to 2 1. So 2 2 is CY square. CY square is 0. Okay, 0 0. Okay, you may check the formula. And for position 3 3 is CX square. 1 0 0. So what we get is K1 is equal to AE. Since we must remain AE as constant, okay, so we simplify this. It is 1 divided by 3 is equal to 0.333. 0.333. So this is 0. This is negative 0.333. 0 0 0 0. This is 0.33300. Okay, and the metric is symmetry. Okay, this is actually the answer, the structure, the element stiffness matrix, and this is for element number 1. Okay, and this is the answer. But most important thing, we have to label this according to degree of freedom. Okay, to label this, we need to refer back to this diagram. Okay, this diagram. Okay, we have to write write the labeling of the degree of freedom. So like this, we have to label. Whenever we want to label, we must always label the near, after that the far. Near, we have near X, near Y, and far, we have far X, far Y. Near X is 1, near Y is 2, far X is 3, far Y is 4. So we call like this. It is 1 2 3 4. It is based on the arrow, because arrow is going to far end. So we label start from near, complete XY, and after that we label far end, complete XY. So we will get 1 2 3 4. 1 2 3 4. Okay. Okay, we will do the same for element number 2. For element number 2, so element number 2, the length is 345 meter. Element number 2, I draw the element. This is element number 2. This is node number 2 and 3. Okay, the arrow is like this. So this will become far because arrow is going to far end. So this is near end. Okay, for the degree of freedom, it is 1, 2, 5, 6. For the coordinate, it is 0, 0, 3, 4. So check, we have node number, we have element number. This is element number 2. Element number, degree of freedom, after that arrow, and we have coordinate. So we have to determine cx, cy, cx and cy. For cx, for x is 3, for x is 3, near x is 0, divided by 5. And for cy, for y, for minus near, for y is 4 minus for near y is 0, divided by 5. So this is equal to 0.6, this is equal to 0.8. And after this, after we determine cx, cy, we establish K2. It is AE over 5. Okay, cx square is 0.6 square is 0.36. Cx, cy 0.48, negative 0.36, negative 0.48. cy square 0.8 square 0.64. 0.64. Negative 0.48, negative 0.64, (0.36), 0.48, 0.64. Okay, this is equal to K2 AE. It is 0.36 divided by 5, 0.072, 0.48 divided by 5 is 0.096, 0.64 divided by 5, it is 0.128. Okay, so this is negative 0.072 with formula. Okay, this is 0.096 negative 0.096, negative 0.128, 0.072, 0.096 and 0.128. Okay, for K2 we refer back to the element. Near is 1, 2, for is 5, 6, so we label as 1, 2, 5, 6. 1, 1, 2, 5, 6. 1, 2, 5, 6. Okay. Okay, we settle the first part, which is element stiffness matrices. Okay, the question is, we need to establish the structure stiffness matrix. structure stiffness matrix, and it is capital K, and capital K is equal to K1 plus K2. Okay, K1 plus K2. So for this, K is 6 by 6 because there are three nodes times 2, total is 6. And for K, in terms of AE, we have to establish 6 by 6 matrix, and it must be written in order. In order means 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, there are 6 by 6 matrix. Okay, from 1 to 6 is all the position. Okay, we find this value from the element stiffness matrices. Let's see, if we want to determine the value of 1, 1, 1, 1, here 1, 1, we have to find 1, 1 in K1 and K2. 1, 1 in K1 is 0.333 plus 1, 1 from K2 is 0.072, and it is equal to 0.405. Okay, for 1, 2, it is 0 plus 0.096, and this is equal to 0.096. For position number 3, 1, 3, 1, 3 is negative 0.333, and no 1, 3 in K2, so it is equal to negative 0.333. Okay, and we will do the same until we find the value of 6, 6. Okay, let's say we want to determine 6, 6 value. 6, 6. Okay, for 6, 6, we find 6, 6 in K1, no 6, 6. We find 6, 6 in K2. 6, 6 in K2 is this 0.128. So this 0.128. If we want to determine 3, 4, for example 3, 4, 3, 4, 3, 4. Example, we need to determine, let's say we want to determine 3, 4. So we go to K1, we find 3, 4. 3, 4, 3, 3, 4, 0. And we go to K2, not 3, 4. So it is 0. Okay, one more example. If it is 2, 5, 2, 5, let's say 2, 5, 2, 5. So find 2, 5 in 1, 2. And 1 in K1, find 2, 5 in K1, no 2, 5. And in K2, 2, 5, 2, 5, 2, 2, 5 is equivalent to 5, 2. 5, 2, 2, 5 is equivalent. It is negative 0.096. Negative 0.096. Okay, I want you to complete this. Okay, I want everybody to complete this. Please follow whatever that I have just shown to you. Okay, so we find the value of structure stiffness matrix, which is 6 by 6 value we find from K1 and K2. Okay, try to do this, and please send me. No, you don't have to send, because the answer is in the textbook. You just have to finish all this and check whether the answer is similar with the answer given in the textbook. Okay, but tomorrow I will give you another question, and I want you to do the same process that I show to you just now, and you have to submit using Google form as usual. Okay, thank you. That's all for today. Assalamualaikum warahmatullahi taala wabarakatuh.